let's start with the introductions. So today we're going to learn about our ECE colleagues so kind of learn about his research. And I joined Northwestern in 2001, and he received his PhD in computer science at University of Texas, Austin. His research interests are in algorithms, formal methods, verification, and their applications to security, machine learning, and a little bit of economy. The latest addition to his teaching portfolio is a course on the Bitcoin technology. He has published over 100 papers. He's serving on a lot of TPCs everywhere I go. He's there. And most notably, among the most recent ones, he is an associate editor of the ACM Transactions on Design Automation. He has received a variety of recognitions, and amongst them, I'd like to highlight the NSF Career Award, the ACM SIGDA, which is the Special Interest Group in Design Automation, ACM SIGDA Technical Leadership Award, and the ACM Service Award. And with that introduction, I leave the floor to you.
Thank you, Steve, for the good words, and thank everyone for coming to my talk. So in this talk, I'm going to actually introduce our recent work on logic encryption for hardware IP protection. As you already know that counterfeit and IP piracy has become a big headache for semiconductor industry. I think the concern is especially very serious, especially for defense department. So I just came back from design automation conference. There we have a DARPA and Air Force sponsored gathering on those issues. So here is actually, I think, a report from ERAI, Electronic Reseller Association, and they reported counterfeit parts. So as you can see here, the number of reported counterfeit parts in the global market is proportional to I think, the global semiconductor sales in $1 billion. So generally speaking, it's roughly among $1 billion of sales, there is one reported, I think, incident. So this is actually constant, kind of like a stable for the last probably 8 or 9 years. So from the same report, is also actually kind of try to categorize the top most counterfeited parts, I think, in 2017. So here, as you can see, so leading actually the categories PLD, so programmable logic devices, followed by microprocessors, analog ICs, and memories. So logic encryption actually is become, I think, a central problem in hardware security. So it could be used to protect against the IP infringement, and also other actually attacks. For example, fab overproduction. So I can explain what is fab overproduction. So nowadays you are doing fabrication, outsourcing your fabrication. So the fab may actually produce more chips without your permission. So in that case, they could actually sell the overproduced chips on the market. And then you could have actually reverse engineering to actually steal your design. Also, Trojan insertion could be also prevented if the attacker doesn't understand your design. So if they don't understand your design, they could not actually insert an effective Trojan in it. So let's look at actually the mathematical definition of the problem. Okay, so here what we are given is a combinational circuit FX with an input and one output. So I think the one output is kind of a simplification. So usually we'll have multiple outputs, but let's just look into the base case with one output. So what you need to do is actually design an encryption circuit. So this encryption circuit has actually M extra input. We call the keys. right? So here, it is a circuit with n plus m inputs and 1 output. And then you want to make sure there's only one correct value that will make the circuit work, or make the encryption circuit exactly the same as the original circuit fx. And also you need to make sure it is robust. That means even though the attacker has actually access to the design of GXK, and also a black box access to fx, it is very hard for the attacker to find the original circuit fx. Right? So here the black box or oracle access actually, I think is due to the fact that the attacker can easily buy, I think, a working chip from the market. Right? So,
So doesn't the working chip implement G though, not F?
The working chip is actually F, because if you have a working chip, you must plug in the correct password. And if you actually break it, for example, if you look into it, then you can see the G function, but it doesn't working because usually I think the vendor will plug in the password into some tamper-proof register. So if you open the chip, I think you cannot see the password.
The password's embedded as part of the production process.
Yes, after the fabrication.
Okay.
Sorry, just a clarification. D is for Boolean or any set?
Yeah, B is a Boolean, maybe, yeah. Any other question? So yeah, I hope we are on the same page, and then I can encourage you to think about how we can actually do this design, right? How can you design the G function?
In your last statement there, I'm a little bit confused as to which of the variables are quantified over and which are not. So I'm assuming that you can't find the function f which takes any input.
Yeah.
Given the function g taking any inputs and black box access to f. Is that what you're saying?
Yeah. So, well, yeah, obviously, if you actually do the exhaustive kind of query into the black box, you find fx, but that's too expensive, right?
So, but this is. I'm sorry. This is.
Yeah. What is the question?
I don't know. I'm confused about your quantification.
So the idea is that I can't give you the circuit for F. I can't find the circuit for F even if I have the circuit for G, and access to something that can compute F for me. I can't actually find the circuit. Is that the?
Right. That's a
That's the-
goal. That's a goal for the attacker. Attacker try to find the fx, and the actually input to the attacker is actually the structure, right, of this encryption circuit, and also oracle access to fx.
But Fx is a Boolean,
Yes.
just one Boolean.
It's like true.
No.
No, it's a function.
It's an n-bit input with a 1-bit output.
Yeah.
And n on a typical chip you're talking about is in the thousands, right?
Right.
Okay.
Right. Probably.
I'm just going by the types. F of X should be a Boolean. F should be a function. F of X.
Yeah, f is a function. Both f and g are functions.
Yeah.
Yeah, as you can see, it's mapping from actually an input to one output.
I think I get it. You can't get the circuit back for F, given the circuit for G.
Right. Yes.
Even if you go buy a production version of F with this tamper-proof register, you still can't get back the circuit for that.
Right.
Right, okay.
Is that clear to you?
You also can't enumerate the whole truth table.
Right. Because enumeration truth table is too expensive, right? So
Right.
we need to find an efficient attack.
I think I understand what you mean now. The notations.
Yeah, but of course, I think the word hard is not well defined, but I think that's one of I think the contributions. We will actually further discuss it.
No, I think the confusion is whether you have to output a circuit for F, or given an X, you need to just output F of X.
Oh, okay, I see. Yeah,
You want the
need
whole circuit
Yeah,
for
whole
it.
circuit. Yeah, of course. Yeah.
If the parentheses were not there after F and G, I think it would be clear, right? So it's hard to find F given G.
Yeah,
That's what you're asking basically.
Yeah.
Because X is-
Okay, yeah. So yeah, the X is actually a variable, so it's not just a fixed X.
You don't want somebody to be able to reverse engineer F,
Right, exactly.
right?
Uh-huh.
okay, next slide.
Okay. Okay. So this has been actually proposed, I think, for more than 1 decade. Okay. So before 2015, I think all the actually proposed solutions are kind of ad hoc, right? So I think if you look at the picture, I think this is a general idea. What they do is actually if you have a fx, which is here, and then they just randomly select some internal signal and then insert a k gate, so it's either XOR or XOR, and then have actually the correct corresponding keywords, right? And then later, they discover it could be actually some of the design could be easily attacked by testing technique. ATPG means actually automatic test pattern generation. So it's actually a technique in circuit testing. And then later they say, oh, in addition to actually randomly select the internal signal, you need to do that more carefully, right? And so I think, generally speaking, all the actually approach is kind of in this fashion, that is carefully, randomly select some signal and then insert the key gate. And unfortunately, in actually 2015, Submarinian et al. Actually discovered a very effective attack called a set-based attack. Right, so the general idea I think is like this. So they actually generate more and more constraint on the actually the key set. Right, at the very beginning, the constraint is actually empty, means actually all possible keys are there, and then each time they use a set to actually find an input. Yeah, let me say with a pointer. So okay. This set is actually used to find the X which can differentiate two possible keys still within the constraint set. And then this X is kind of important because by actually querying the oracle and then set up actually the equation like this. So on this given input, this encryption circuit must give the same value as actually returned by the oracle. It is constrained the key, right? So generally speaking, at least one of the two keys will be actually excluded. So this is kind of like a keep ruling the possible keys within the constraint set until there is no such actually differentiation, right? So that means either you have only one key left, or you have multiple key left, but they're given the same actually output. Means they're all correct keys, right? So then you solve actually the set and the constraint, and then you get actually the correct keyword. Okay, so I hope the idea is clear.
So in this type of system, does the attacker know the difference between the inputs X and the input bits X and the key bits K, or are they kind of are they distinct separate sets, or are they actually kind of intermingled? So does an attacker know the difference between an input and an input bit and a key bit?
Yes. That's assumed, but because by reverse engineering, if you open the actually chip, you can see which connections are come from actually the tamper-proof register that you identify those as the keys. Right. So yeah.
How big is the key?
Usually the key number of key bits is actually kind of proportional to the regular inputs.
Okay.
So here M is almost equal to N.
So when you look at the chip, right, this is, you scrape off the top, take the picture, get the transistor,
Yeah.
then scrape another
Yeah.
layer. Just keep doing this.
Yes. Yeah, that's kind of a reverse engineering.
In this loop you're running here, are the K and K1 variables?
K1, yes, they are.
And so SAT, it looks like if you give it a formula, it tells you what the variables are that make it true. Is that what's happening?
Yes, that's correct.
But somehow,
Yeah.
first while, are the K and K1 the while variables, or are they not variables?
Oh, they are variables. Generally speaking,
If you run SAT and you only got an X out.
well, yeah, this is kind of like a simplification. So generally speaking, you get actually assignment to X, to K and K1. But only what I'm concerned is actually only the X. So I only extracted the X. I just ignore the K and K1. So the assignment including K and K1, but due to I think the algorithm, it will not use K and K1 assignment. So generally speaking, you can see here I have extracted actually X, K, and K1, but I ignore them.
And then you evaluate F on the.
Yeah, the extracted.
The bits that satisfy this formula?
Yes.
And so that last thing you've added is just G, X, K is equal to true or false, whatever X, F
Yeah.
happens to be.
Yeah.
And also I substitute in X hat for whatever its true false assignment is.
Uh-huh.
And I simplify the G X hat K to be just a, okay.
Yeah, it becomes a constraint, not K, only a Boolean, not K.
And so the point is, this attack is practical, you can actually do this.
Right.
Yeah, so
Should I believe that, right? I mean, I don't know.
you're doing this SAT problem for every bit. So you do the SAT problem, if there's K input bits, you're gonna run the SAT problem K plus 1 times, right? Each time to get one new set in the C thing, and then once at the end to get the.
No, it's not just one bit. You just actually have one constraint. It's a Boolean kind of constraint there. So it's constraint probably pruning more than 1K out of it.
It could potentially be 2 to the size of the number of key bits.
Yeah, it could. Yeah, but unfortunately, because the conventional, I already talked about this. They do the design very ad hoc, and it's blind on how actually it will behave, right? So I think the news is actually all existing logic encryption up to that year has been actually defeated, totally defeated. Okay. So that means it's practical. And also there means one thing, that is each time you put a constraint into it, it's pruning not just one, right? So I think it is guaranteed pruning at least 1K, but I think the reality is it prunes a lot of Ks each time you have a constraint.
So the point is, there's some special structure of the way previous constructions were making these circuits. And because of that special structure, the SAT-based attack works.
Yeah.
But you're maybe hoping to give us a different construction where the SAT-based attack is not gonna work, even though you could potentially run the exact same algorithm.
Yeah, exactly. Okay, so people already actually, I think 1 year after the attack, they proposed, I think, a different design. Okay, so there are two of them, SAR lock and anti-SAT. It's two promising solution. I think here is actually a SAR lock. So the general idea is like this. Okay, so they explicitly design actually the arrow kind of in the encryption circuit, right? So the encryption circuit is actually XOR of the original circuit and a kind of flipping, right? So this is kind of a different circuit, right? So the idea is actually I'm going to actually flip the output if the K is equal to X. That means, okay, so each actually run K is only run on one input X, right? So in that case, then when you actually query the X there, it only excludes one run K, right? So therefore, it is make sure that the SAT-based attack will run into exponential iterations. Right. So this is, I think, a simple idea. So here, of course, you have a mask because you need to have a correct K. So if K is equal to correct K, then you don't flip. Okay, so there are two problems, I think, for this, approach. The first one is actually, it has an extremely low error. Means for each one run K, there is one error. right? So all the actually inputs will generate the correct output, but there is only one input that will make a difference, right? So I talk about the problem with actually the extreme low error, and also the structure is vulnerable because you cannot just actually give this as the encryption circuit because then I think the attacker can simply look at the structure and say, oh, this is actually the original circuit and take it, right? So you have to do some obfuscation. I think what proposed here is actually some resynthesis. So I'll talk about that later.
I'm sorry, is extremely low error bad or is extremely low error good?
Bad.
Oh.
So it's bad for the actually designer, so good for the actually attacker. So I talk about that, right?
Why is it good for the attacker? Because if there's only one input that differentiates,
Right.
it's harder to find.
Yeah, let me tell you, yeah. So this slide actually talks about the evil of the extreme low error, right? So what you can do is actually you can do approximate attack. That is, you don't care you get actually the correct key, right? Even I run K, I plug into the encryption circuit, and then I'm pretty sure I can sell the chip to the market because the customer cannot find that error, right? Right? Think about this, right? You can still fool the market. And also this is even bad because there is actually a wrong kind of error plug into actually the chip, right? So you can imagine that when a user actually buy the counterfeit chip, someday it may actually make a kind of a crash your system, right? So this is something kind of it's as a byproduct, it actually embedded a stealthy Trojan in the design, right? So this is, I think, even worse, I think, than I think the normal IP piracy, right? And then there are some others. For example, if actually the attacker or the user actually by accident find that error, then you can do the bypassing. You can hardwire the correction, right? Because you know, okay, so plug in one wrong key, there is one input that will produce wrong output. Then I just correct that one. Then I get actually the working circuit, right? So this is called a bypassing attack. So generally speaking, no error number is bad for the designer.
So just to summarize the last few slides, the SAT attack is if there are many errors to be found, I can easily check keys that are wrong, and that's sort of the idea with the SAT attack.
SAT attack is actually kind of try to find the input that can differentiate actually at least two keys.
Whether the keys are right or wrong.
Right.
And now you're saying these other approaches have very few wrong inputs, so that's also a problem because it's going to work most of the time.
Yeah.
Yeah.
Right. That's right. Yeah. So I think people already, when they propose SSR lock, they already kind of feel that the low error number is a problem. So they try to actually combine. They say, oh, I'm not going to use SSR lock actually alone. I'm going to actually combine the SSR lock with the conventional, right? Remember the conventional one may have actually a large error number. So I combined it, right? So therefore, I think they also propose some ad hoc. So here, I think the point here I want to raise is actually, I want to find a solid foundation, not just a cat-mouse chasing, right? Because if you propose a defense and later somebody will propose, I think, attack on it, right? It's not good, right? So I think I want to actually do some kind of theoretical study to make sure that you will never get attacked, right? So here, I think the way I'm doing this is to try to capture the whole design space, right? So if you have a fx, then what is actually the gxk, right? The function, the encryption function. What is actually the whole design space? So here, if you look at this, then what really matters is actually the difference function, right? That is actually the dxk, which is defined as the difference between g and fx, right? Because that's how you do the query and then proving the wrong key, right? So I'm here only focus on how to design this, right? So how to design the difference function. If you look at this difference function, you can do Shannon decomposition and then get, I think, a two-dimensional truth table, right? So generally speaking, I only distinguish the regular input on the rows and then the key inputs on the columns. And then since this is actually what we call error matrix, it's one entry is one means actually this combination of x and k will actually generate a difference. Right? One means a difference, 0 means actually not the same. Right? So if you look at this, then generally speaking, it becomes a matrix design problem. Right? If I want to design encryption circuit, probably I need to look at the truth table and then design the error matrix kind of carefully. So here, we can actually define error number, I think, on the matrix, right? So for each column, the number of ones is actually the error number on that given key, right? And then we define actually the error number for a whole matrix, or the minimal error number among all run keys, right? Because that matters, right? Because if you consider approximate attack, you don't want actually any k that generates a very low error number. Right, so we use actually the minimal number among all the columns as actually the minimal as an error number definition. And then if you look at actually attack complexity, we define the attacker complexity as how many actually inputs you need to query in order to find out the key. Right? Well, generally speaking, to find out F, there are two ways. You can either find actually the password K star, or you can do the by parsing find F. Right? So this is actually the attacker complexity, meaning what is actually the number of queries I need to do on the oracle in order to find out the correct key.
But they have more than the oracle, right? I mean, they have the actual multi-level logic design.
Yes.
So
yeah, they could get more information from there. So I talk about that. Very, very good, very, I think, insightful, I think, comments.
Oh, I see. Maybe you're coming to that. So I was going to ask, how is the matrix related to this? But maybe.
Yeah, well, I'll explain. Yeah. So generally speaking, then you can generally speaking, the attacker complexity is the unit covering problem, right? Because what you need is actually you find the subset of rows to cover all columns with one unit. This is a unit cover problem. So here, as you can see, I want to first talk about the minimal cover problem. Right? So even though actually you can, if you look at the stack-based attack, the stack-based attack may not be able to find the minimal cover, right? Because it will probably start with a random input, and then starting from there, right? Even though each time it will find actually the input that has to cover some new key, right? I think the SAT guaranteed that each time you find a key, the key will actually cover at least one new wrong key, right? But still, I think theoretically, the minimal cover problem gives you a lower bound, right? So we want to look into that, right? So this is kind of animation to say what is the cover, right? So here, as you can see, these two subsets cover all actually rows with one unit, right? So therefore, it is actually a cover, a row cover for this matrix, right? I hope this is clear.
Sorry, what is covering what?
Yeah. So here this shows actually these two rows is the minimal cover for the matrix. If you assume everything else is zero, right? Because even though this is actually symbolic, I have a dot there. So just to only look at actually the.
What about the one that's on the?
Yeah, it's covered because this column has many ones, but there's one covered, therefore it's covered. You don't need to cover everyone. A column is covered if at least one of it has been covered, right? Because when you think about this, when you query this input, then since this is one, the difference, and then the constraint will exclude that k, right? So this k here is no longer
So the third column has all zeros in it.
Yeah, you must have this. Yeah, this is k star. Yeah, it's basically put a k star there, so it has all zero in it. Okay, so this problem is also has been actually, I think, started by mathematicians. Because if you look at this, this is the same problem as actually the mean cover of hypergraph, right? Because you can treat actually the rows as the edges and then the columns as the nodes in a hypergraph, right? So therefore, this is actually a hypergraph covering problem. It has been started, I think, by mathematicians, I think a long time ago. Along, I think in 90s, actually gave a band, upper band like this. I think probably the message you get is actually 2 to the power of n plus 2 to the power of m times log m. M is the error number divided by m. Right? So I think later, Chivato and the co-author have another actually, I think a similar band. But the exact band is still open problem. So it's, yeah. If somebody is interested, could look into it. But I think for us, this is not very useful because I already told you, the minimal is only give us a lower bound, right? So the set may not find the minimal cover, right? So here, I think the first result we actually get is actually to study the average, so average attacker complexity. So what we do is actually we look at if we do the random query, so we don't even actually do the we allow the replacement. Means actually we just randomly query the input and then put those constraints into the set solver. If you look at this, generally speaking, we can show that after m times 2 to the power of n over m random queries with very high probability, you already covered all the columns. Okay. So that means actually this is something we can probably hopefully achieve, right? If you have actually m as an error number, you cannot hope you have a very high attacker complexity. Okay, so then I think I can skip this one. This one, yeah, we can study all the actually conventional encryption and then find that are really bad, I think, on those matrices. I think the good news is since we model this problem as a hypergraph covering problem, right? Therefore, we can actually leverage the result, I think, in the hypergraph design, right? Generally speaking, if you have a hypergraph with a very high actually mean cover, then we can use that for our design. But unfortunately, this is not the case because if you have a truth table, the truth table may not actually turn out to be a polynomial time actually implementable in circuit, right? So, generally speaking, we cannot actually use the hypergraph result, even though we can say, oh, whatever you get in the hypergraph research, we can actually translate that into the encryption design.
One second, isn't it a property of F as well? I mean, for different.
No, it's not. It's independent of F. Because here, think about this. I only design the difference.
So here you're thinking about F like in a disjunctive normal form or something like that, right? Where it basically is the truth table.
No, usually we actually have the input of fx as, I think, a circuit. It's a netness.
Sure, I mean, the design is a multi-level.
Right,
So
yeah.
Does this result imply or depend on thinking of F as disjunctive normal?
Actually, yeah, if you look at this, really, the design is independent. As I said, it's independent of fx, right? Because I think at the very beginning I talked about this design only actually concerned about the difference. It's a dxk function. dxk is defined as actually gxk not equal to fx. So it's independent of that. Really, it's independent of fx. Yeah, later I will show you that's the case. Right, so yeah, I think just the next state slide is actually the design. Okay, so I think the good news is actually we can find a very good actually trade-off with actually efficient circuit implementation. Right? So the idea is like this, right? As you can see here, I only design the difference circuit. So generally speaking, this is what I design. I only design actually this part. This is your FX, right? So if you do XOR with your FX, then you get the G XK, right? So this is the DXK. And then this is just mask, means, okay, so if the K is the correct password, then I don't need to flip, right? But you generate the difference, I think, using this circuit. Right? This simple circuit is like this. So you XOR the regular input with actually the K input pairwisely, right, using XOR. And then you have actually HV, which actually generates actually the error, right? So what you need is actually you want the unset, right? Unset means actually the input that generates 1, right? So you need the unset number, the size of unset for this function to be m, right? So that means on m different input, you generate actually the wrong output, right? That's 1. 1 means actually the output is different from actually FX. As you can see here, the design is really independent of FX. Right.
But don't you give this circuit to this is the final circuit?
No,
Oh.
you cannot.
Okay.
Right.
Because
The same problem. If you give this to the attacker just fetch FX. Right. So So then this is kind of instantiation. So what we can do is actually we make the error number and the attacker to be exactly the same, right? Because one of them is 2 to the power of n divided by m, one the other is m, right? So you make them to equal, then we can actually have a design meet in the middle, right? So this is actually design. The edge function is here, like this. Of course, I think we need randomness, right? Think about any encryption method need randomness. If you don't have randomness, then attacker just look at your algorithm and then get the result.
Wait, so if you go back to the previous slide,
Uh-huh.
what exactly does an attacker see here?
Oh, the attacker will see the function, the same. This is the function that attacker see.
Right.
But it cannot see the structure. So I talk about, because in order to do that, we need obfuscation. We need to actually hide the structure.
So we're going to do another transform.
Yes.
We're not going to see this exactly.
Right, exactly. So we do actually 2 steps. First, we actually design this, and then we do a obfuscation, do a transformation. So you cannot see the structure. You have the same functionality, but different structure. Okay, so then, I think we can introduce randomness here. Right? So I think that's easy to see. And then I think look at actually the way we do this is we try to increase the number of queries you need to do to the oracle in order to find the correct key. So here the other way, I think a minor thing is you can also making the SAT harder, right? So we can making each instance of the SAT solving harder. So in that case, we need actually one-way function, right? The reason why we need the one-way function is because we need efficiency in the encryption circuit, right? We cannot afford a difficult function in the, forward direction. But when we do the SAT, it's kind of solving the problem in a reverse ordering. So know the output and then try to figure out what is the input. So we need something called a one-way function, and we need a very efficient one. Right? I think before me, some people talk about using actually encryption, for example, SEC circuit, but it is too expensive. So here, we just propose to use GoldRex function. So if you know GoldRex, kind of candidate for one-way function, right? There's no proof. Because nobody knows where there exists a one-way function. But he proposed actually a candidate, right? So here, generally speaking, you have M input and M output. You make actually the input-output form an expander graph, and then you can actually have, the simple function, right? So it's XOR of actually all the random D input, except you have one pair doing actually AND, right? So, and we actually plug in the one-way GoldRex function into our design, and then we tested this by actually run the SAT-based attack on it. Right? So here there's 2 set of experiments. One is without one-way function. That is actually the original design without one-way function. As you can see, actually, the attacker time is actually exponential in terms of the input length. And if you plug in the actually one-way function, the runtime increased dramatically. Right. Okay, so I think this is the question you ask, right? We cannot give this to the attacker, right? Because simply, the attacker can grab fx from this structure. So therefore, the logic encryption is actually two problems merged into one. One is locking. Locking means actually we allow the attacker to do behavior analysis. Think about the set and query-based attack. It's actually behavior analysis. I don't look into the structure, right? Only look at the functionality, the behavior, right? So this is locking. We need actually a robust logic locking, and also the structure, we need to hide the structure, right? So structure hiding is also known as obfuscation, right? So I don't know whether any of you have seen this. This is a program, a C program, I think obfuscated C program. I think it's a champion of, I don't remember which year. There is actually a competition on C program obfuscation. And then this is 1 year's champion, right? So probably you can try to figure out what is the function of this C program, right? So obfuscation is actually kind of a very common practice in software engineering for a very long time. But it hasn't been started by theoretical computer science. And it only actually, I think, started by this paper. Barak and co-authors in 2001 actually prove that if you design the obfuscation as a virtual black box obfuscation, means you cannot see anything. You just see actually a black box here. Then it's impossible. So there's no such a virtual black box obfuscation for general program, right? Of course, I think the domain is actually the general program. So therefore, they define indistinguishability obfuscation as a substitution, right? So indistinguishability obfuscation means if you obfuscate two circuits from the same family, then the obfuscated circuits are computationally indistinguishable, right? So that means they look randomly the same, right? So they are two, of course, it's efficient algorithms. So it's efficient probabilistic algorithms cannot distinguish the two obfuscated circuits. And then later, Goldwasser and Roseblum.
They're not required to actually be the same function. They just have to be hard to tell they're different functions.
I think in their definition, the family all have the same function.
Oh, okay.
Yeah. The family is defined as actually circuit from of the same function. Okay, so then later, I think Goldwasser and Roseblum come up with another definition called the best possible obfuscation. So I think I gave a simple proof. I think this is probably too simple. So for combinational circuit, then this best possible obfuscation can be achieved by resynthesis. That is, if you define actually the resynthesis in a general way. That is, you change the structure, but you never change the functionality. Right? That's resynthesis. Then it can be achieved. However, we cannot use actually logic synthesis. There are tools doing logic synthesis, but there are many developed for optimization, right? So they try to optimize, make the circuit simple. But obfuscation means we need to make the circuit kind of more complex, right? So it's there's no tool actually that can achieve this, and this actually has been shown, I think, in a recent research. I think in recent research, people have done actually resynthesis to do obfuscation, but people later find that it can be easily attacked. Okay, so there's a breakthrough, I think, in the obfuscation field. So in encryption community, this is considered as a breakthrough. So in 2013, Gog and the co-authors actually proposed a candidate I/O solution. Right? It's not provable, kind of secure, but it's a candidate. for the I/O. But I think the Arpon actually and the co-authors started the practical implementation of this technique and find that it's just too expensive. So the most complex circuit that can be obfuscated by using this method is just a 16-bit point function, right? So it's kind of, unfortunately, too complicated to be applicable in our application, right?
1 second. So, I mean, it is provable assuming a cryptographic assumption called multilinear map assumption.
Right, I agree.
Okay, yeah, it is provable.
Okay, thank you for
Yeah.
clarification. So here we just follow the role model, right? We feel that the indistinguishability obfuscation is a good way to define, because how can you because there are all possible attack method, right? How can you exhaust all of them, right? So I think using the computational distinguishability is the best way to capture all the possible attacker behavior, right? So therefore we just follow, I think, their role model to define something called ILO, right? So this is have a indistinguishability logic obfuscation, right? What's the difference? The difference is actually here we allow to use K inputs, right? The reason we need to allow use K input is because in hardware IP protection, if you don't have a K password, then I don't care. I don't want, right? If I don't understand your circuit, I can still steal it, right? Because I can reproduce it and then sell it, right? So I think as a byproduct of actually hardware IP protection, I can always use actually kind of protected keys, right? So with this, generally speaking, we find that this ILO is actually simpler than IO, right? IO is too expensive. So I think probably you already see what is the solution. The solution is actually a universal circuit. So generally speaking, a universal circuit is a circuit that can implement any function from a given family by fixing the values on some selected input, right? So generally speaking, you have actually the input, one part is called programming inputs and the other is actually regular inputs.
So what's an example of a family of circuits?
Yeah, it's, I will give you an example later. Yeah, next slide. We'll give you the family is really important, but yes.
And in terms of like being able to choose a family or choose a function within a family by fixing values, I mean, so that's like a multiplexer circuit would do that, right? I mean, if you have like circuit 1, circuit 2, circuit 3,
yeah,
and the
kind of
multiplexer,
yeah.
Okay.
Yeah, but you want the universal circuit to be efficient in some things, right? If you do the max,
a multiplexer,
right?
It's like one layer,
right?
So.
Yeah. Okay, I'll give you. Yeah, I think that's a very good question. So I'll give you an example, right? So actually, the two classical papers, one by Volin and one by Cook, right? Both of them are Turing Award recipients, right? So they proposed, I think, Volin proposed, I think, a universal circuit for all circuit of a given size n, right? So for any circuit of size n, I can design a universal circuit, and this universal circuit has only n log n size, right? Theoretically, it's efficient. And then Cook and Hoover later actually developed a universal circuit with the same depths. I think this is extremely important for, I think, engineering. Because in circuit design, actually the depths is actually kind of decide the performance, right? The delay, the performance. So this one I think is more interesting, but the cost is higher. So of the circuit size C, it will do C cube D divided by log C, right? So it's much higher than this one. Of course, if you are theoretician, then maybe this is good enough, right? It's efficient. But as an engineer, it may not, right? Because here we can see the key bit length is actually linear in the universal circuit size. Means actually each gate in the universal circuit has at least, I think, a constant number of programming bits. Right? So that's compared with our original goal, it's probably too much. Okay. So because of this, then we discovered there is a trilemma, I think, in logic encryption. So I talk about this. Logical robustness means actually the attacker complexity. We need actually attacker complexity by using the query. And then structural security, you know what's that, right? Because you want to actually hide the structure. And then there's efficiency. Efficiency here means the size of the circuit and especially the size of the key input. You don't want to have a large key input, right? So generally speaking, we want to achieve, I think, a good solution on every one of them. But if you look at the existing solutions, we were not there. So the holy grail of the logic encryption hasn't been achieved yet. But if you look at the kind of traditional, right, this is a preset traditional solutions, it achieves structural security and encryption efficiency, right? The reason is because by actually randomly select the signals, they don't introduce extra structure in the circuit. Therefore, it's a structurally secure. And also, the number of bits, k bits, they introduce is also very efficient. For the post-SAT design, because we explicitly design the kind of locking behavior of the circuit. So this one is actually secured, and also the number of k bits we introduce is actually also small. But as you can see, right, the structure security is not there yet. And then universal ones can achieve both locking robustness and the structure security, but the encryption efficiency is not achieved. So we have actually kind of three categories kind of solution, but none of them actually really solve the problem, right? So our effort is try to solve this one. So one approach we propose is actually something called a convolutional circuit. We try to design some semi-universal circuit, right? So here, as you can see, this is we have layers of AND gates, and then we have a kind of a convolutional connections between the layers, right? So here, in this example, each gate has actually a fan out of 3 to the next level of gates, right? Of course, if you look at each of these connection, it has actually 2 K gates on it. One is XOR, one is OR gate, right, with actually corresponding K bit, right? So generally speaking, this one is used to program the polarity of the signal, right? If you have 1, then you change polarity. If you have 0, it does not change the polarity, right? And then the OR gate there is used to kind of program the routing, right? If you have a 1 there, then the connection is break. And if it's 0, the connection is there, right? Of course, for this one, I really, this is, I think Peter has a question. What is the family? For this semi-universal one, I don't really know what is actually the family, right? It's hard to capture. But so what we do is actually we try to test this out. So what we do is actually we come up with a convolutional circuit, and then we randomly select the programmer bit, and then give this to the SAT-based attack to see how efficient it can find out actually the k bits, right? So there are 2 sets of experiments with that. One is called Fouquet. Fouquet means actually every program bit is treated as k.
So for the convolutional circuit, as long as that first 2 layers are wide enough, right? I mean, you can capture any combination circuit.
Yeah, I could. Yeah, I think we need to probably look at more deep into that. I think so far we don't have any theoretical proof. Yeah.
Is this the same graph as last time?
No, it's different. Yeah, it looks similar, but I can tell you it's different. Right? So generally speaking, the growth is actually exponential. And then there are 2 of them. One is actually if you treat every program bit as a k, of course it's more difficult to attack, right? So if half of them actually is exposed explicitly, then it's easier. But still, they grow exponentially. Right. So I have a few. Let me see. Yeah, just a few slides, and then. Yeah, we're still not there. Even you use this one. I think the thing is actually, if you count the number of actually Ks, even in the partial K, the number of Ks is still too much, right? So maybe I think the rule of thumb we use for the number of Ks actually, it should be a constant times the number of regular inputs. For example, if you have n regular inputs, probably up to 3n k inputs, maybe that's a good kind of criteria, right? So it's still too much. So then we try to actually look further into it, and then we find that we can find actually a kind of a partial holy grail, but it's only for a spatial circuit. So generally speaking, we find that if your original function fx is really unbiased, biased means actually the onset and offset are very different. Means actually either you have a very small number of input that generate 1, or very small number of input that generate 0. If that's the case, then you can simply do the encryption just on the primary input. So on the primary input, you just do the XOR of the k bit with the original input. Then we can prove that this one has an average attack complexity, almost achieve the best trade-off we have shown. Right. So I think this is kind of good news, and then of course we are still missing actually I think at least half. That is for unbiased functions. How can we do this? Right. This is actually kind of a quick. So we have a very simple function which is given here, which is biased, and then we run the SAT-based attack on it. Yeah, it shows that. Confirms that we need exponential iteration to attack it. Okay, so in summary, I think the things we got here is actually we find that the logic encryption should be looked into actually two separate parts: logic locking and structure hiding. And then we found that there is a trilemma among actually the locking, the obfuscation, and the efficiency. And then mainly our result come from actually two parts. For the logic locking, we find that this is actually can be totally captured by the error matrix design. And then I think there is a lateral contention between the attack complexity and error number. And then we find a good locking scheme. We also have a very good design with a linear overhead to solve this problem. So generally speaking, we can treat this as a solved problem. And then we look at actually obfuscation, and we found that universal circuit can solve this I-low problem, but still, I think for engineering, the overhead is too high. So then we propose a convolutional circuit and also some efficient, very, very efficient solution for biased functions. So for the future work, I think probably the biggest open problem is actually, can we find efficient solutions for unbiased functions? And then engineering-wise, we need to develop actually programming algorithms for the convolutional circuit. I think the testing in our convolutional circuit is kind of cheating because we just have the convolutional and then we randomly select the program bit. And then we say, oh, this is our original circuit, and then try to attack it, right? But I think in reality, you need to start with a target circuit and then try to program it into the convolutional circuit. So there is a big, I think, probably half of the domain I haven't touched. It's called cyclic logic encryption, right? So the idea is like this, right? If you look at actually the encryption circuit we talk about, the encryption circuit we talk about is still combinational circuit. Means there's no cycles, right? But why not introduce cycles by using the keys, right? If you're using the keys to introduce cycles in your circuit, it's probably even harder for the attacker to attack it, right? So this is, I think, a whole, a domain for logic encryption. It's called a cyclic logic encryption. So in this field, we have done, I think, one work to develop a very efficient SAT-based attack, right? But you need actually more things in the attack algorithm. It's called a SAT. And then Roselle from our group also developed more robust cyclic encryptions, I think, in that domain.
So just to be clear, this is the type of circuit, this is still combinational logic, so you're just waiting for it to settle, right? There's no latch or anything, right?
No latch. There's no latch.
So
Yeah.
basically just, hit it and it'll eventually settle.
Right. So if you give a run, think about this.
What if it's an oscillator? What if it's actually a circuit that's designed to to give you a cyclic
Uh,
output.
yeah, let me tell you. Okay, so the thing is actually if you give a run k, then the behavior of it's really strange. It could be stateful, means actually it's kind of like a state sequential circuit. That's a state machine.
Sort of,
Right.
yeah.
So for the correct, so generally speaking, what you need to guarantee is actually for the correct k, it is always actually kind of will behave. Right. So combinational.
So it needs the sub.
Yeah.
It needs the sub.
Probably it never. Yeah, I think it never generates actually kind of. You don't need the settle time.
Okay.
Or what you can do is think about this. You have a correct case will just break the cycle. In a correct situation, there's no cycle in it. Right. Uh-huh.
I think I missed the relation between randomness and the solutions you described.
Uh-huh.
So do you rely on randomness? Do you inject randomness in the circuit?
Yes. Yeah, I have to. For example, yeah, if you look at actually, yeah, I think previously I talked about the run. Yeah, this is I think this is solution. So here, for example, the pairing of the actually regular input and the k input could be actually random. Also, you could actually randomly insert actually inverter here. So that means you could use XOR or XLOR. Right, because if you always use XOR, then the attacker knows your algorithm, then you can actually figure out. But you actually randomly introduce a bubble, right? So bubble means inverter somewhere among the actually inputs. Then that's randomness. And also, this HV is also can be random. Right, what you need is only actually, the onset is actually of the size M.
And you need to guarantee that the randomness will not change the behavior that you have.
Right, that's guaranteed.
So, at some point you mentioned that there is a goose chase where basically people are trying to fix SAT with ad hoc techniques. I'm wondering, did you try the system with other attacks that are stronger than SAT? And how does it behave?
Yeah, I think for my design, I proved that even you don't use the SAT, you use a random query, right, based approach, it's still secure. Yeah.
Right, I mean, so some of this, I mean, there's a whole area of functional encryption in cryptography, right, which tries to address many of these questions. And I mean, there are like solutions like garble circuits that are used for coming up with ways of obfuscating circuits and.
This is a garbled circuit.
No, but there are formal ways of. No, I was just wondering how it compares against these things, and I mean, it seems like you're using many ideas from cryptography as well. So I was just wondering if there is a. I mean, is this a form?
So your question is whether there are other probably techniques from cryptography research which can be borrowed. I think we exhaust. Well, I should say I spend a lot of effort looking into that, and I think what we presented here so far is actually the best we can get.
Okay. But this is also, I mean, is there a? I mean, so I guess you call this logic encryption, and I guess it's functional encryption. Is it fundamentally different, or is it really the same thing?
Fundamentally different. Yeah, some people feel that it should not call logic encryption. They say, oh, in cryptography field, they use logic encryption for some other things. But in our field, I think there are three terms they used interchangeably. One is logic encryption, one is logic locking, and one is logic obfuscation. So I prefer to use logic encryption because, if you look at actually my research, I kind of feel logic encryption is actually composed of locking and obfuscation. You need both. So that's why I think, maybe it's better to use logic encryption and then differentiate actually locking just for the behavior kind of security, and then obfuscation for the structural security.
A couple comments, or questions. One technique that's used in ciphers, for example, is to modify the key as the process goes on. What's your thoughts about building, for example, a sequence or some kind of modification into the key part, and then, of course, that makes the combination with the regular inputs to produce the output a little bit more complex, but it may also make it more secure.
Yeah, I think that's a very good question. So I think we actually look into it, but I think what we discovered is kind of like, okay, so if you introduce a sequence of keys, I think kind of in the state machine, because here you need actually the concept of states. And we find that if you do that, you can translate that sequence of actually input kind of into a key, I think, in the combinational situation. Probably with actually the key much larger, right? So think about this. It's kind of like flattening. So if you have a sequence of keys, then I can put the sequence of keys actually as a long vector of keys, and then just use that, I think, in the combinational circuit. Yeah, we look into it, but I think so far the conclusion is it may not help.
Well, the second question was about obfuscation. A simple obfuscation is to put extra, in your case, extra circuitry in there that actually doesn't participate in the final output, but is just in there and makes the analysis a little bit harder. Have you thought about that?
Yeah.
Okay.
Right. Yeah, I think the general idea is there, but you need to avoid actually kind of introduce a structure, right? So I think if you look at the universal and the semi-universal, the idea is actually, don't actually introduce any structure in the circuit.
So if you want to encrypt, if I gave you, let's say, like a 64-bit ripple carry pattern, say, how would you encrypt it? What would be this? I know it's kind of a weird animal.
Yeah, very good question. I think it's probably better if you actually translate that into a gate level design, right? Because if you look at actually what we have.
So I build a bunch of FAs and chain them together.
Right. Yeah. And then there's, right. And then we can do it. Yeah. So what is your main concern for the carry?
I'm just curious what the approach should be. When I design this ripple carry adder, what would be the process?
Yeah, what I'm thinking is kind of make that into a gate level design.
Because it doesn't quite, I know, but it doesn't.
It's very
regular, but it's very long.
Yeah.
Right, so it doesn't necessarily fit into a convolutional model.
In that sense, probably I need to actually make a big convolutional circuit with many layers. The layers should be probably accommodate the carry chain, right?
What is the typical energy and power overhead of, for example, the convolutional approach?
Yeah, I think we didn't actually do that analysis, but I think that's something we need to do. I think convolutional, generally speaking, probably is very expensive. Yeah. That's why I think we need to look into, I think, a more efficient approach.
Thank you.